writing the rate law implied by a simple mechanism with an initial slow step. So the key to this kind of question is realizing that the slow step is the rate determining step. And each of these steps are both called elementary steps. And the rate law for the elementary step is going to match the rate law for the overall equation. So whichever elementary step is the rate determining step, that rate law will match your overall rate law, which we up until now have only been able to derive experimentally from data for the overall reaction. That's because the slow step is what affects how quickly the reaction actually happens. The fast step is poof, it's over, right? So it's the slow step that actually determines the overall rate law. So first of all, what we need to do is we need to write the overall process that is happening. The way, which you will have learned in Gen Chem 1, in order to balance overall reactions from reactions that occur in multiple elementary steps is search for the intermediate. So remember, an intermediate is something that is formed at the end of one elementary step and then gets used up at the beginning of another. So formed as a product from one elementary step, then used up as a reactant in a subsequent elementary step. So the key is that the amount of moles in your balanced chemical equation for each elementary step is going to cancel out the amount of intermediate. So I'm looking for something that's formed at the end of one step and then used at the beginning of the next step. So I can see that dinitrogen monoxide is formed at the end of elementary step 1 and then gets used up at the beginning of elementary step 2. So the key to balancing this is make sure that the stoichiometric amounts of the intermediate, in this case the dinitrogen monoxide, are going to cancel out in the overall equation. To actually write the overall balanced equation, I'm going to just add everything on the left-hand side of the reaction arrow is going to be a reactant in my overall equation, and everything on the right-hand side of the reaction arrow for each elemental step will be on the product side of my overall equation. So you can do the same rules as you do with mathematical equations, that is, cancel terms that appear on both sides of the chemical reaction and gather like terms. So from step 1, we've got H2 gas plus 2NO2 gas. State symbols are important because for to gather like terms or to cancel out things that are spectator species and they don't appear in the overall equation, they do need to be exactly the same, and that includes state of matter, right? Then step 2, we have H2 gas and we have dinitrogen monoxide gas. So that is all our reactants that are present in step 1 and step 2. So then we're going to stick in a reaction arrow, a little bit like that. Sorry, it's not very pretty. And then on the right hand side, so step 1, we have N2O gas plus H2O, also a gas. And then from step 2, products, we have N2 gas, dinitrogen, and water gas. Okay, so that can be simplified. So the first thing you should notice is that your intermediate will cancel out, which was our N2O gas, bish, bash, bosh, bye-bye, there you go. The next thing you should notice is that we have some like terms that can be grouped together. So the H2 on the left-hand side can be grouped together. The H2O on the right-hand side can be gathered together. So my balanced overall chemical equation will be 2H2 gas plus 2NO gas, forming intermediates cancelled, 2H2O gas plus N2 gas, and you can go ahead and check, count up all your numbers of atoms, etc. That should be beautifully balanced. So write the experimentally observable rate law. So you can write a rate law for each step, right? Rate for step 1 is going to be K1, and then based on the reactants, it'll be H2 to the power of 1 because it's first order in H2, and then it'll be NO, and then that'll be to the power of 2 because there are 2 nitrogen monoxides in the balanced chemical equation. So that is going to be for elementary step 1. You can also go ahead and write a rate for elementary step 2, right? So K2, and that'll be the concentration of H2. Again, that's first order in H2 times the concentration of dinitrogen monoxide, okay? But in this case, we know that the rate determining step is step 1. Therefore, the rate law must be the same as what it is for step 1, okay? the rate law of the slowest elementary step is going to match the rate law of the overall equation. So we've already got rate equals k, so we can just go ahead and put H2 first order, and O will be second order. So I'm going to just tidy that up and make that look pretty by using the right parentheses, etc. So that'll be NO power 2. So there we have it. That is how we do that for a simple mechanism with an initial slow step. It's always going to be the rate law from that first elementary step, because that is the rate determining step.